Hello and welcome to our webinar, Safety and Security with Contract-Based Design. I'm Thomas Schütz and I'm an aerospace engineer with fable for embedded software and for tool chains and formal methods for building embedded systems. So what is it all about? We're talking about safety and security. We have very special requirements for that. Especially the robustness of the system must be good in order to be stable for safety and security systems. Contracts are a very nice way to help with this kind of problem. So what's the problem? The problem is, imagine, for example, a traffic light. You have a traffic light in one direction, and at the crossing you have another traffic light, and if both are green at the same time, you will have a problem. You might run into an accident and so on. So that's a typical safety critical problem. So let's focus for the beginning on the safety critical topic. So how can we avoid this situation in a complex software and in complex systems? That's always the question. The first thing I have to do is I need to describe what I want to avoid. So how do I describe what do I really want? Very often we have textual requirements or specifications. For example, in this case, requirement 1, the two traffic lights must not be green at the same time. Yeah, so that's not very formal. I can understand that, but how can I express this more formally? And now, when I describe this, I need to prove that it's true. So how do I do that? That's the second step. How do I prove that my system really fulfills this requirement? I can write test cases, unit test cases, integration, acceptance tests, hill, mills, hill, pill, and so on testing. The question is, how do I prove that my test case is sufficient or that it's right? Or so this kind of question, because the test case itself is very complex usually. So how do I prove that my test is correct? Well, that's the second question here. And when I'm testing, I usually test very late in the process. During the coding, in most embedded systems, tests are not performed during coding, maybe some unit tests and so on. But most problems are introduced during coding or even earlier in the requirement phase. But they are usually found very late in the process. So how can I find these problems earlier? Ideally, even in the requirement phase or in the specification phase. Now imagine you can describe what you want, and you have models or code that implement what the system needs to do. And now, if you could describe what you want as a formal contract, so more formal than just a textual requirement, and through some magic mechanism, you could verify your application, that your application actually does what your contract suggests. That would be a very nice thing to do. And that's what the contract-based design is all about. So I have a formal contract, and I prove by some mechanisms that my project or my code actually does what it's supposed to do, not what it does. So that's the idea behind the contracts. Let's start with a classic contract design by contract. It has been introduced by Bertrand Meyer. He designed the programming language Eiffel. And the basic idea is to describe pre and post conditions, invariants, and side effects to define the semantics of functions and classes. So on a class level, on a function level. So it's basically a formal specification of interfaces for functions and classes. And it can be theoretically verified formally or during runtime, depending on the mechanisms you have, on the languages you have, and so on. Languages like ADA and Eiffel support definition and validation of the contracts for functions and objects, and that's very valuable. ADA you might know maybe from the field of avionics. Eiffel is not very well known, but it also supports contracts. But in many avionics projects, ADA is used. So that's a nice proof that that contracts actually can work really good. I give you an example in the language C. You can use, for example, asserts to implement contracts. So it's not very formal, but it's a way to implement contracts during runtime for runtime verification. In this case, for example, if you have a function like square root, you want to make sure as a precondition before you actually calculate the result, you want to make sure that that the argument is bigger or equal 0, because if it's below 0, you will have a division by 0 error. So your program might fail. In this case, the precondition checks the incoming parameter. Then you call the square root functionality. Now it's safe to call it because you know it will work. And the post condition is the result needs to be also 0 or bigger than 0. And now you can return the result. What the assert does, that's another question. Does it shut down the program? Does it throw an error? Whatever you want to do, you can do at this place. The point is here to completely separate the pre and post conditions from the netto content, from the actual meat of your function. That's a very valuable approach, but it's very fine-grained. The problem with bigger systems is that you cannot make, let's say, a bigger functionality safe by creating contracts for every little functionality. So in a bigger context, that usually is too fine-grained. The problem with the classic contracts for embedded systems is it only works for functions and classes on unit level. It does not help with asynchronous concurrent systems, integration, system level tests, and so on. That's a real problem. It's very fine-grained. So imagine you have a huge project. You might put a lot of effort in many contracts. So probably that's not the most efficient way to handle this kind of approach. And another problem is that the classic contracts do not have states, they do not have history, they do not have a possibility to check execution orders or timing, so things that are really highly relevant for concurrent asynchronous embedded system. So asynchronous systems, that's really hard to test with contracts. So let's have a look at contracts on a higher level. That's what we do in many environments. We use, for example, state machines as interface contracts. We also have legal execution trees. That's another method. But a state machine is a very elegant way to define an asynchronous interface contract. And this can be used on any level of hierarchy. That's what it makes it so valuable for bigger systems. So let's start with a little example. Again, C code, because it's very common to use C code and everybody knows it. So imagine you have an API in a language C. So you have 6 functions. Your module, your C module, can be called upon. So initialize, start, stop, and so on. So now, if I ask you the question, what do I do before I need to call function 1? So I might need to initialize the component, and I want to start it. and then I can call function 1. So that's an assumption. It's not specified here. It's just without any order. It's just a flat API. So now if I stop, do I have to reinitialize, or do I have to trigger start again to call function 1? So I cannot answer this question based on the information I have here. So that's why we introduce state machines as interface contracts. So it's not the implementation state machine of the functionality. It's just sitting at the interface and describing what is allowed. So in the interface, I have to call first initialize, then I'm in the initialized state at the interface, whatever my component does internally. And then I need to call the start function. And then I can call function 1, 2, 3 as often as I want. If I call stop again, I cannot call the function 1, 2, 3. It just doesn't work. And I do not have to reinitialize the system. I just have to call start again, and then I can call function 1, 2, 3 again. So it's a very, very simple specification of what you're allowed to do at the interface level. So the order of execution, even timeouts and things like that, you can describe 100% what is allowed. Everything else is forbidden. So you only need to describe what is allowed. That's the idea here. And if you describe what is allowed, and if I reduce if I have a look at the possibilities I have, the combinatorial possibilities I have to call those APIs without the contract, I have, for those 6 functions, I have 720 different ways to call them, orders to call them. So I have theoretically 720 test cases I need to run to really test completely every order that's possible. If you make a reset and call it another one and another one, you're very fast in the range of billions or trillions of theoretical paths through your system. If you only need to test what the contract allows, because you have a means to avoid the rest, then you only have 6 paths through your system. So you always need to initialize and call start, and then you can call any order of execution here, and then the stop. So that's really simple to test completely, at least for in depth 1. Even depth 2 or 3, you could theoretically test all the orders of execution. Here, that's not possible. Here you're already in the range of, I don't know, hundreds of years or maybe billions of years or so. So first of all, you have a very nice way to describe what is allowed. That's also very nice documentation for anybody who wants to use your interface. And you get a massive reduction of execution paths or internal states in the protected area, orders of magnitude. This enables much simpler systems and better testability, for example, by testing complete path coverage. And it's a very, very effective way to specify your interfaces for anybody who wants to use this interface. So now I need to make sure that this works, of course. So what can I do now with the contract? So first of all, I can specify with the contracts really nice interfaces and generate their documentation. That's the requirement phase. Already very valuable because you always get a correct requirement according to the contract. The contract is much simpler to describe than just text. So then in the early stages, you can use a formal verification. So if you use model-based development, you can use a formal verification based on the model, state machines, and the like. So in the design phase in your model, you can use formal verification if you have modeling tools that allow this or that enable the formal verification. Not all the tools enable this. Or there are not many tools that enable this actually. So the next phase in your development is testing. You can use a contract to generate test cases. That's a dynamic test phase. So you can generate test cases that try to break your system by generating all the things that are not allowed, or also to prove that everything that's allowed is actually tested and works correctly. So that's a very elegant way to generate test cases. And the last thing I want to introduce here is to use the contracts to generate robust interfaces or monitoring for runtime verification. So you protect your interfaces. Doesn't matter on which level. It can be a system level, can be a component level, can be a even fine-grained a class level or so. But you verify this during runtime, and this way you can protect, for example, a part of your system against attacks from the outside or against wrong implementations of something you do not have under control, like a public interface or interface to another component provided by somebody else. So that's a very good way to make sure during runtime that your system does what it's supposed to do. It's also very effective way to generate code, for example, for redundant monitoring of safety critical or security critical issues. So you get a really redundant and diverse implementation of the monitor of your system health, for example. So now I'm going to give you 3 little demos of methods we have and we use for our customers in projects. So that's all real world projects. Demo 1 is a formal verification. So step 1, formal verification, and the implementation assistant in a modeling environment we developed. You develop the structure model. For every interface, you have an interface specification. So that's the API, if you will. So it's a bidirectional asynchronous interface specification because it's an asynchronous distributed system here, machine control, for example. And additional to the interface specification, you have a contract, interface contract. In this case, that's not an interface state machine, something similar. It's a legal execution tree that defines the allowed order of execution of calls at the API in both directions. And then you can implement your functionality, your behavior of a component as a state machine. And in the state machine, you get a formal verification, and you have an implementation assistant that makes sure that every contract is fulfilled on model level. So, and when you generate the code, you can be sure that it does what it's supposed to do according to the contract. You can always make an error in the contract, but it's really hard to get it wrong in the actual implementation then. And the contract is much simpler than implementation usually. So that's the first demo I'm going to give you. The second demo is contract as a black box test specification for combinatorial state transition tests, for SIL and HIL tests. So the idea is you define a contract. It's a so-called state transition test. Basically, it's a black box behavior description of the allowed behavior and of the forbidden behavior at the interface. For example, for a hardware in the loop test or for a software in the loop test. And that's a very compact description of the expected external behavior of a component or of a complete system. And from there, we generate all the needed test cases to prove that all the paths are correct or wrong, depending. So you also can generate not only the good paths, the happy paths, but also all the forbidden paths to make sure that all the forbidden paths are tested as well. And imagine now, that's a very compact description. Imagine now you generate, you create those test cases manually. That's a lot of work. So you have a formal description of the black box behavior of the system as a contract, and you generate the test cases for all the paths and data combinations you need to cover. Second example. We use this, for example, for our mini-hill test system to make sure that the system is robust for long-running robustness tests, to explicitly test all the data combinations, all the path combinations, to bring robustness and safety into your system. The third demo I'm going to give you is the generation of a monitoring contract for runtime monitoring. We have an IDL, interface definition language, with contracts, and we generate runtime monitoring for C code or for other languages. It's pretty simple to generate code also for other languages. And the idea is you have this interface definition language, you generate and you also describe the contracts for those interfaces, the typical classical contracts, so the data ranges and so on, but also the interface state machines. So we can handle this on both levels. And then we generate the interface monitoring. So that's the monitor header, the monitor implementation of the interface state machine, and the header for the service implementation. Of course, you need to implement this on your own. So that's the manual part. You need to implement what it's supposed to do, but everything you need to compile and run the contract is generated automatically from the contract description. So the client is, so we generate the monitor to sit between the caller, the client, and the service implementation. And now when I compile this and run this, you get for every single call the proof that it's correct. And if it's not correct, you get for example, in this case, a sequence diagram that tells you exactly what happened, where you called the wrong function, in which order have the functions been called, and so on. So those are the three demos. Now I'm going to jump into the first demo that's on model level. So here I created a little component. So that's, for example, here in this case, that's a motor control component. The motor component can handle a start move to position, answers with a done move to position, and I can stop it, and then I expect a stop. But that's only the description of the API. Now I can describe the semantics. Here you can see on a start move to position, I expect either a done move to position, or if it's not done yet, I can call a stop. I can stop it while it's working. But when I call stop, I need to handle the stopped functionality. And here I can describe more and more messages, more rules, and so on. And by that, describing formally what is allowed. I could also attach timing constraints for the answer and so on. So that's a typical contract for such a component. And same with the timeout. I can start and stop a timeout. I have also defined the timeout semantics here according to what I expect here. So, and you can imagine there are a lot of components that use timeouts. So why not checking them all? So now let's jump into the behavior. Let's start from scratch. So now I have a state machine and I want to start a motor. So let's start a motor. Here I have the motor and I want to move to position 1, 2, 3. Okay, now I started the motor. Now I immediately can see I could send a stop, but I have to, and that's not optional, that's mandatory. I have to implement the transition to a done move to position, because that can happen at any time. So now I click on that, and the assistant helps me to implement it correctly. So that's now it's correctly implemented. Here in this state, as long as the done move to position reply has not haven't received, I could at any time stop the motor according to my specification. So now, as a good programmer, I say, okay, it might fail, so I want to call a timeout. Let's call the timeout 1, 2, 3. It's, let's say, 1,000 milliseconds. After 1,000 milliseconds, I want an error. So now I start the timeout. Now I see immediately, you can see this very good, that whenever I start a timeout, at any time in the complete chain here of events, the timeout might occur. So it could occur here. Now, if I satisfy this timeout here, it still could occur here. So what do I want? Do I want to kill the timeout, or do I want to satisfy the timeout tick here? So in this case, when I'm done, I want to kill the timeout. So I'm going to kill the timeout. So that's my decision. I want to kill the timeout. And now the contract is satisfied here. It holds. In this case, when I get the timeout, and imagine now the motor takes longer than a minute, longer than a second or 1,000 milliseconds, it's still running. So I either need to stop the motor, or I need to react to the dumb moved position. So in this case, as an implementer, I say, okay, now I have an error, I want to stop the motor. So that's my decision. So I stop the motor. Now it stops, but now I must react to the stopped transition formally, because that's what I described in my contract. Now I could make a self transition that's probably more efficient here. I want to stay in the error state. So this would be, for example, an error state. Okay, so that's basically the development on model level while satisfying all the contracts. So if you define contracts for all the interfaces, and you've seen that's pretty simple to do, even for bigger interfaces, every use of this interface is checked in the model on model level, if you're using state machines, of course, in this case. So that's the model level verification. That's the so that's a really, really nice way, because you avoid errors even before you produce them. So the next example would be during testing time. So that's the second method I'm going to show you. That's the interface. That's the state transition testing approach. So basically, you create a contract as a state machine, again, with a little different focus. So it's not only for the interface, it can be used for complete systems or complete components. And you describe basically all the states and all the paths and the actions your system can do or is not supposed to do as a black box behavior. So it's a description of a black box behavior. And for example, in this case, I say, okay, I want to, I could call the system with different speeds, and I could take different paths through my system. And for example, here I say, okay, I want to make all the boundary values. So I add 1 and I add 99 to my system. So you see the contract is changed. So it's programmed textual, and the diagram is generated. And now I generate from this, I can generate the test cases. I'm doing this on command line now. Generate the documentation here and the test cases, of course. And now you can see here, for example, I have generated 25 test cases. And here you see the test cases for 1 and for 99 I just added. And if I want deeper tests, I go higher with my metric. It's an end switch metric. I won't explain this in detail, but I'm going to show you what happens if I'm going higher with the metric here. So instead of n switch 1, I'm using n switch 3. So it gives a much deeper combinatorial generation. I'm generating the system again. So of course, the code that executes the test cases is also generated. So, and now I have even more test cases. I have, I don't know, something like 163 test cases to test all the combinations of data and paths in my systems according to the contract and the depth of tests I want to generate. So, and they're all generated and executed automatically. And now I can run the system. I have this on my desktop here. That's the Mini-Hill system under test, is a microcontroller here in this case. It's basically a small hardware in a loop system. And the generated test cases are running here together with the environment simulation. And now I'm going to start the test execution here. I run the tests and I introduce an error here probably. So I'm pulling a wire to simulate an error here. So, and down here you see all the state transition tests. Those are the combinatorial tests that are running now. And in the end, you get for every executed test cases, you get a sequence diagram that tells you exactly what happened, what went wrong. For example, if I click this, I go back into the IDE, back to the step in my contract, basically where something failed. So that's test time contract code generation or test case generation with contracts. And now I give you the third example. The third example is a contract approach where we have an interface definition language. That's in this case, it's a C interface. Could also be for another language. Here you can already see the classic contracts, the ranges that are allowed, and so on and so on. So the pre-post condition side effects and so on. And here you can see the interface contract. So if I add something else here, so for example, a new transition here from processing to processing something else, from processing to begin, for example, you can see now I created this additional path here. That's of course not what I want. And now if I run the system, so it's automatically generated. It generates the code for the checks. That's and for the interface state machine. So the code is automatically generated. Now if I run the system, it compiles the contract. It compiles my system. It integrates directly with C code in this case. And now I see, okay, the contract failed. I did something wrong. I have an invalid transition from current state processing with trigger start processing. Okay, but let's have a look at the generated sequence diagram here. So that's the generated sequence diagram, and you see exactly that I call start processing in the state processing. So let's have a look at the actual. So I call start processing while I'm already in the state processing. So that's obviously wrong here. So let's fix this. Give it another try. So now it's generated again, and now I'm okay. So let's have a look at the result again. Everything is clear here. So those have been my examples. We have many more technologies where we use contracts. If you're interested, yeah, feel free to contact me, of course, to discuss this for your use cases. So what are the typical use cases for contracts? You want to protect your system at the external interfaces. So imagine you have a middleware or some kind of system, and you want to protect this against incorrect behavior of other systems, of surrounding systems, users, for graphical user interfaces also, but also for attacks. Basically, you make the keyhole much smaller by having a formal contract. It's really hard to break this contract if you apply this during runtime. So that would be an example to generation of interface monitors, also for safety critical systems. If you want to implement complex behavior fast and correctly, you can use the model verification and implementation assistant as an example. You also can generate redundant, diverse implementation of safety monitors for your safety critical system or for your security critical system. So you can specify the safety rules completely redundantly with a contract and generate the runtime monitors. You can also find bugs that are really hard to find. For example, sporadic race conditions, something that happens once a year for one customer, one of your thousands of customers. You can specify the expected behavior and generate a lot of test cases, combinatorial test cases, and try to break the system and to find those sporadic errors and reproduce them to really be able to detect the error and to debug the error. And you have many other use cases. So that's it. I hope it was interesting for you. If you have any questions about the contracts, don't hesitate to contact me, and we can organize a call if you have any questions, and we can discuss the use cases for potential use cases for your project. Some of the technologies are open source, some of them are closed source, some of them are just methods we use. We can coach you, for example. So please tell me what kind of problem you have and what would you like to solve. Thanks for your attention and have a nice day.